All right, we're going to start looking at all the different types of quantity takeoffs by looking at earthworks. So earthworks are major civil works. And in this section, we're going to look at how to measure all of the key earthworks quantities. We'll talk about the different types of earthworks drawings and specifications, the basic concepts and definitions you need to understand, and how to measure each of these key quantities. So to start with, we're going to talk about the different earthworks drawings and specifications, and we're going to go through a sample earthworks design package and look at all the typical drawings you'll see and what types of drawings you need to be familiar with. All right, so let's go through a sample set of earthworks drawings. So you can see this project is for some earthworks as part of a golf course, and the project is to construct this new berm along the edge of the golf course as part of flood protection. So like the first drawing is just a general overview and layout of the site. The next drawing, we've got a more detailed drawing that shows the orientation of the berm, and it's also given us these distance markers. So these distance markers are often referred to as chainage markers, and for any longitudinal project, they'll show you what the proposed structure is going to look like at each of these points. And there's also a section view A and a drawing reference, so C317. So if we go to C317, section A, we'll be able to see a cut of the berm that shows the exact design. So we go to this drawing, which is C317, section view A. We've got a typical elevation of the berm. So it shows natural ground level, so existing ground level, then the design for the berm, which shows a 1-in-4 batter with a 10-foot road on top and compacted fill. And then we've also got these diagrams, which were often referred to as cut and fill diagrams, which show a longitudinal section of the berm, or if it's a road, it would be a longitudinal section of the road, and each of these chainage markers, STA 397, refers to a point in the berm. So that's that STA 397. So you could imagine this berm mapped out along these markers. If you're looking at it horizontally, will show you the actual design for the berm. So these diagrams are really useful for working out cut and fill volumes, because we've got our existing ground level as the dashed line and then the finished level. So we can take difference between these two levels to work out the actual cut and fill volume we need to complete. So just to summarize, we've got our layout or orientation drawing, we've got our profile drawing, and we've got our section view. So if you're talking about earthworks drawings, you're talking about a road, you'd get the exact same three drawings. You'd get a layout of the road, which is useful for orientation and understanding the set out. Then you'll get a profile drawing, which shows existing ground level to finished ground level. And then you'll also get a section view. And you can use these three drawings to calculate all the key quantities you need. And there's also some other drawings showing this sedimentation basin and other elements. But if we're talking simply just understanding earthworks drawings, it's really just this layout or orientation view, this profile view, and this section view. And you can use these three to calculate all the key quantities you need. Next, we're going to talk about some basic earthworks concepts and definitions. So if we're talking about an earthworks quantity takeoff, first thing you need to understand is cut and fill. So you'll hear these two terms thrown around all the time when people talk about earthworks. So cut is another word for excavate. So it's basically the process of removing excavated soil from an area to lower the elevation. And then there's fill. Fill is the opposite of doing a cut. So it's adding soil or rock to a site to raise the elevation to the desired level. So when we talk about earthworks quantities, they'll always talk about cut volumes and fill volumes. The next is swell and shrinkage. So swell is when the soil is excavated, it occupies a larger volume because it's not compacted. So when you dig up soil from the ground, it loses its compaction, so it swells. On the opposite is when you fill material, the volume of the material compresses as it's compacted. So basically it either swells or it shrinks. And then there's standard factors we apply to different materials. So if we're talking about clay, there might be a 15 to 30% swell and shrinkage factor. Silt, there might be 12 to 20%, and sand, there'll be 8 to 15% because the material is more granular. So it compacts and swells less. Next, we're going to look at, on our sample Earthworks design package, how to measure these key quantities. The key quantities we're going to need to measure are our volumes, so our cut and fill volumes, so the amount we need to excavate and the amount we need to place. Then we'll also need to look at mass hole diagrams, so these are the distances we need to move the cut and fill material. Topsoil quantities, so if we're talking about new excavation, the amount of topsoil we need to strip, the amount of spoil we're going to need to remove. So this is when there's a difference. Say we're moving the same material from one area to another. If there's an excess that we're excavating over what we're filling, then there's going to be a volume of spoil we need to remove. This is our overburden. And then also we'll look at some trenching and excavation quantity takeoffs. So in summary, Earthworks quantity takeoffs are really simple and straightforward. We're basically working out the amount of dirt we need to move from one spot to another. It's basically as simple as that. All right. So now we need to turn this set of drawings into the key Earthworks quantities that we can use to schedule and price our project. So the first thing we're going to do is we're going to open an Excel document that is going to be used for our Earthworks quantity takeoff. So we'll put Earthworks BOQ. Within the table, we're simply going to list out the key quantities we're going to measure. So we're going to clearing and grubbing, so topsoil removal. We're going to note down our cut volume. We'll call excavation, volume, placement volume. So clearing and grubbing. This is the amount of topsoil we're going to have to remove for our project. And this is actually quite an easy measurement to take. So now, for me, this set of drawings is actually is hard to use because they're all imperial measurements. But some of you guys are in the US, so you might prefer this, you might find it easier to look at this set of drawings. So all we're going to do to calculate the clearing and grubbing, so this is the amount of topsoil removal, is we're going to look at this typical section view, and we're going to assume that the widths of this berm, we're going to have to make some assumptions around the widths of the berm, and then we're going to be able to get the lengths of the berm from this plan view. And we'll assume we'll have to strip 100 mil of topsoil. So put that down as a comment, 100 mil of topsoil to be stripped. And then what we're going to need to work out is the length of the berm multiplied by the width, and this will give us the area. So if we make a worst case assumption and assume the width of the berm, so if the top road is 10 feet, then we'll assume a 1 in 4 batter. And if the average height of the wall, which they're giving us here, we could take the average of these numbers and work out an average height for the wall and times it by 4, which gives us, because it's a 1 in 4 batter, we know the height of the wall will be 4 times the width. So this is actually another useful tool you can use Bluebeam for, you can go File, Export, Excel Workbook, Page Region, and just select that. And basically, you can just export a table in Bluebeam to a set of measurements. So once that exports, it's given us these numbers. We can just take this average, 8.9 feet. So if our height is 8.9 feet, we can note down, I'll just write this here, average height So 8.9. Then the width is going to be, or I should be more accurate in that description, length of batter, say, was 8.9 times 4, so 35.6. Now, I'm going to convert these to meters, because feet, I find feet confusing, so we go 35.6 feet is 10.85 meters. So now I know the total width of berm is going to be 10.85 plus 2 plus 3. So 3 meters is that road at the top for the golf cart. So if you look at that, we've measured that's on average 11 meters. That's on average 11 meters, and we're allowing 3 meters for the road on the top, which gives us a width. Should I close that? Gives us a width of the berm on average of 24 meters. So then all we need to do to get the clearing and grubbing area is get the total length of the berm, which we don't even need to measure. We can just go off these chainage markers. So it starts at 0. To 50. Or you can use the scale, which is 1 to 200. So go tools, measure, collie length. And I'll just map out this. Map out this berm. Scale is 1 to 200. And then again, it's given me the unit length in millimeters, which isn't that useful. I want meters. So it's 128.24 meters. Total width of the berm is 28. I'd actually put in another column. What was it? 128 meters. And the width, 4.7. So a bit. So area. So actually I'll rename that measurement. So our clearing and grubbing is 3,161 meters square. The next is going to be our excavated volume. And so we can look at the profile and we can pretty clearly see that wherever we're looking, the existing ground level is much lower than the top of batter. So there's actually going to be no excavation. So we can mark this as 0 meters cubed. Now we need to calculate our placement volume. So this placement volume is going to be the amount of compacted fill we need to place along this entire profile. The easiest way to calculate that, well, what that is in practice, that's going to be the difference between the top of the berm and the existing ground level. Okay, so the average height between this point and there. We could do this by measuring the average, calculating the average height of the wall the entire way along the profile, or we could just use the data that they've provided us, which they've given the actual height of the wall at each of these separate points, which we already put into, exported to Excel to give us the average height of the wall. Now I actually noticed an error in how Bluebeam exported the data. They didn't have a decimal place between the 7 to the 2, which is why we're getting an average height of the wall of 9 feet, when in practice, it was actually meant to be 3 feet. So it's actually something you have to be careful with in Bluebeam, that sometimes they do miss these little, when you export something directly to Excel, sometimes they'll miss things like little decimal places. So we've got an average height of the wall of 3 feet. So we'll update this to 3, the correct measurement, and we'll get average height in meters is going to be 0.92 meters. Now, what we need to calculate is for this berm, based on an average wall height of 3 meters, what is the area of fill we have to place per meter? I'll just close this quickly. So the way we'll do that is we'll calculate the area of the berm, which is going to be, the berm is going to be made up of 2 triangles and a rectangle. So the area of a triangle is half base by height, so it's going to be 0.5 by the base, which will be the height of the wall, by the length of the batter. It's going to be this times 2 plus this box in here. I think that's how we're approximating the shape of the berm. It's really 1 rectangle and 2 triangles like this. So it's a pretty rough approximation, but in the absence of more accurate survey data and a 3D model, it's probably going to be a pretty accurate approximation. So we get that. That's the triangle. Let's get the rectangle. It's going to be that 10-foot golf cart, which is 3.048 meters by the average height, 2.8. And if we get area, it's going to be 2 times this plus this. So that is the area of berm. So then if we multiply that by the length, we get the placement volume, which is the length by the area, which is 1,636 meters cubed. What we should factor into this is placement for that 100 mil layer of stripping, because remember when we cleared and grubbed 100 mil, we're actually going to lower the natural surface level by 100 mil, so we should factor that in. We're at that volume by the depth, 316 meters cubed. Then we also have to allow that we're going to be placing compacted fill. So we're going to lose some of the volume due to shrinkage when we compact it. So if we allow for a 15% compaction, it will be the sum of these times 0.15. So an additional 200 meters cubed. So total placement will be the sum of these, which gives you 2,200 meters cubed. So what are the key quantities? We've got to strip 3,161 meters squared of topsoil, and we've got to place 2,245 meters cubed of soil. And that's the key quantities we need to complete this Earthworks project. All right, so the final type of civil takeoff we'll look at trenching takeoffs. So trenching sometimes confuses people, but I think it's by far the easiest way to do the easiest item to do a civil takeoff for. So for example, this is the type of drawing you get for a trench. So this is for high voltage cables. So it shows the power cables, 3 power cables. There's a control cable, communication cable. There's a sand bedding. Then above that, there's a protective cover. So these are sometimes like plastic high voltage cable marker tape that's put above the cables. There's sand and cement, and then there's base course and a road surface. So to do a takeoff from this trench, you'd first need to know the length of the trench. So you'd get that from the plan views, which shows you could easily calculate, say it's 100 meters long. And then this is if you can imagine, that's looking down the trench, what it's meant to look at. So you then just simply go and per meter calculate. This drawing doesn't show you enough information to be able to work this out, but if you knew the depth of that, the depth of that, the depth of that, then you just work out per meter how much of the 14:1 sand cement mix you need, how much of the 20:1, how much of the base course. So we assume that, so the depth of the cables is 900 mil. If we can just simply assume that that's 300, that's 300, that's 300. You just break it up into 300 mil sections. Then for your takeoff, you work out how much you need per, call this material per meter. I mean, the other thing, it doesn't show you the width of the trench, but if we assume the width is 0.6 meters, so you need, of the 14:1 sand and cement mixture, we'll assume it's got 14:1 cement. Oh, my spelling's off today. Sand/cement. 300 mil depth. Then the volume of that you're going to need is going to be the width times 0.3. So it's 0.18 meters cubed per meter. So that's the metric you use for trenching, meters cubed per meter. For 20:1 sand cement, then it's going to be the same. It's 0.3 deep by 0.6, 0.818 meters cubed per meter. Base course, again, assuming 300 mil depth, 0.18 meters cubed per meter. Then we're also going to need marker tape, and there's 2 separate runs of marker tape. So we're going to use, so per meter, we're going to need 2 meters. And then protective covers, we say it's 200 mil widths, say it's 3 200 mil widths of cover, we're going to need 3 meters per meter. Then basically, to get what we need for 100 meters, you just times all these numbers by 100. That makes sense, because they're all meters cubed per meter or meters per meter. So for 100 meters of trenching, we're going to need 200 meters of marker tape. For 100 meters of trenching, we're going to need the 14:1 sand cement mix. We're going to need a total of 18 meters cubed. And it really is that easy. Trenching, I think, trenching quantities is super easy to work out. You just need the trench profile view and the length of the trench, and that's it. And this same principle can be applied to drainage trenches, electrical trenches, communications trenches, or other utilities.